Hello and welcome to our section 2.1 lecture today. Today we're starting a new unit that's going to use some information from before, but this one is diving into a new idea. Definitely not a new idea in geometry. It's kind of where a lot of it originated from, and that is parallel lines being cut by a transversal. So in order to approach this and get started here, we've got a couple definitions that we're going to start with, and then a lot of the ones I've actually already written for you. We want to think of parallel lines are lines that never cross. Okay, they never intersect. I want you to think of them as crossing as opposed to touching, because lines don't just touch. When you kind of have that idea of lines touching, you might have some kind of visual like this, that one line approaches the other one, and then it sort of ricochets off. That doesn't happen with straight lines. They either cross or they don't. So we want to think about straight lines whenever we talk about lines. So they never cross. Now, thanks to advancements in computing software, and not even that big of an advancement, I would say, it's pretty easy to somehow draw parallel lines. It's a little harder if you're trying to do it by hand, and I think it's important to be able to do it by hand just to give yourself a quick sketch and to understand what your picture is trying to say. To show that lines are parallel in a diagram by hand, we'll throw in a couple extra arrows in the middle of a line, those two symbols there, since there's the same number of arrows on each one of those. They each have one. They could each have multiple, and that would mean that they are parallel to each other. If we were going to do that with writing, like if we were trying to write out something that these two lines were parallel, if we had them named, I just have them L and M here, we would say that line L is parallel to M, and that's the notation that we would use. Okay, that symbol there of two vertical lines means that the two lines are parallel. In order to approach the topic of parallel lines cut by a transversal, we probably need to know what a transversal is. Kind of my best visual for it is to use the idea of a city road system. I'll pick on a couple roads that we have in town that run parallel to each other. I'm going to look at Virginia and Newmark. Those are kind of the Newmark, not New Make. Those are two of the bigger ones in town that probably a lot of people travel on every day. And if I want to get from Virginia to Newmark, since they don't intersect, there's no intersection of Virginia and Newmark, I need something to go over to get there. And there's plenty of options. I'm going to pick on another very common one, and that would be Broadway. Okay, Broadway is right up from the school. A bunch of traffic lights on there, so it's probably an important one. So in this diagram, Broadway would be our transversal. It's our way to get from Newmark to Virginia. Okay, so it's a line that is going to cross two, we would say, or more lines. And the key here is that it crosses those at different points. Now, that's obvious when we talk about parallel lines. Hold on, let me write it, then talk about what I mean. Transversals exist outside of the parallel line world. We don't need to have parallel lines to have a transversal. But if we don't have parallel lines, then we need that transversal to intersect them at different points, and that's what gets us from the one line to the other. If all three lines cross at one point, then it's not technically a transversal. But when we have two lines that are parallel, any line that intersects the two of them has to be at different points. Okay. So let's take a look at some of the angle pairs that we have within parallel lines being cut by a transversal. The first one would be corresponding angles. I'm going to throw some shorthand ways to write these right in here. We would say corresponding angles. That's a very common way to shorthand that. I don't just want to use like two letters. Maybe you've done that in the past, like CA for corresponding angles. I want a little more context to what we're talking about. Okay, and it says that they're angles that are on the same side of the transversal and the same side of the parallel lines. Realistically, I want to look at, if I am looking at, let's say, this angle right here. I actually want to change colors for that. If I want to look at this angle right here, I'm looking for the same location, the same relative location in the other intersection. Okay. So another way I would think about that in my analogy here is I would think about the corresponding being 7-Eleven, the store 7-Eleven at the corner of Broadway and Virginia, and I don't know, you could pick anything in that little shopping center on Newmark. I'm going to say McDonald's, McD's. Okay, those are corresponding in those two intersections because they're in the same relative location. They're both in the northeast of that intersection. Okay, so I do think it's important to know what the definition is, but I think what's easier to relate to is some sort of diagram example. We're going to use the numbers of the angles in this diagram to come up with examples that kind of help us. So if I pair those up, I have 1 and 5 are both in the top left. Let's go ahead and start with those. Angle 1 and angle 5. Also, we have 2 in the top right. We have 6 in the top right. So those are another pair of corresponding angles, 2 and 6. 3 and 7 also match up. And 4 and 8 also match up. Okay, those are all pairs of corresponding angles. Now here's the big result. When the two lines are parallel, all those pairs of angles are congruent. Angle 1 is congruent to 5, 2 to 6, 3 to 7, 4 to 8, meaning they have the same measure. It's the same number of degrees of an opening. Okay, we're going to say that they are congruent. Okay, those angle pairs are all congruent. The next one we'll talk about is alternate interior angles. Here we would say alt int angles. Okay, they're angles that are on opposite sides of the transversal between the parallel lines and not adjacent. So if we're looking for that, let's say we have McDonald's here is on the interior, and really it comes down to everything in between the two parallel lines is called the interior. Everything outside of the parallel lines, here and here, is called the exterior. It's all about the angle's relationship to the vertical lines. Back to my example, my analogy here. From McDonald's is on the interior of the parallel lines. Its alternate interior would be on the other side of the transversal and at the other intersection. So it would be like Rite Aid. Okay, McDonald's and Rite Aid are alternate interior of each other. Okay. So as far as the angle pairs in this diagram that are alternate interior, we have angle 3 and angle 6, as well as angle 4 and angle 5. These pairs of angles, the big result that we get here, sorry, hold on. Gotta take care of something. These pairs of angles, if the two lines are parallel, are also congruent. They have the same measure. Okay, so those angles are congruent. All right, 3 is the same size as 6, and 4 is the same size as 5. The next one we have alternate exterior, so we'll say alt x. Oops, not alt x. We want to throw that t in there. Angles. They are angles that are on opposite sides of the transversal, outside the parallel lines, and not adjacent. Okay. Technically, all the things in that definition are needed to say it verbally, but it's a little bit easier than that. We might think in my analogy here, we've got 7-Eleven on the exterior of the parallel lines, and its alternate exterior counterpart is AutoZone. Right, the auto parts store just down the hill there. Okay, those are alternate exterior of each other. In our diagram here, we have angle 1's an exterior angle, so it should have an alternate exterior angle to it. It does. It's angle 8. So we have angle 1 and angle 8. Also, we have angle 2 and angle 7. Are also alternate exterior angles. These two, they match everything else. They are also congruent. Okay, angle 1 is the same measure as angle 8, and angle 2 is the same measure as angle 7. The last one that we'll talk about here are consecutive interior. For an abbreviation, we'll say cons int angles. Okay. Another way you may have heard of these before is same side interior. I don't really like that name. It's not official enough for me. It's a little lazy of a way to say that for me. So I'm not the biggest fan of that. I realize now you can't really see that. I'm in the way. But same side interior. It's a good way to think about it. Okay. I don't have a great analogy for this going back to my diagram here because so many things have closed down. I would say Rite Aid and Sizzler. That is now closed down. It was either that or Jim Vick Auto Sales and McDonald's. So you pick. It doesn't really matter. But both of those have since closed down. So it doesn't quite make that much sense. But those are consecutive interior to each other, and those kind of give us an idea of what the consecutive interior angles might be. Now, this one's a little bit different because we're looking still interior, and we're looking on the same side of the transversal, so we're going to have angle 3 and angle 5, and also angles 4 and 6. Now the question is, how are these related? They're the first one that's not, and then first one and only one, that those two angles are not the same. Does angle 3 look the same as angle 5? It doesn't. I've got a big angle 3, like more than a right angle, and angle 5 is less than a right angle. But they do add up to 2 right angles. They add to 180 degrees. So we'll say that they add to 180. That's a little bit tough to see. 180 degrees. Okay. Now, the amazing thing with all this is as I look at this, there's 8 angles there, but there's only 2 different angle measures. Okay? That's what it really comes down to. From everything that we've said so far, let's say angle 1 is, 60 degrees, just throwing a number out there. Well, we've said angle 5 is the same as angle 1. We've said angle 8 is the same as angle 1. And we probably have something a little bit older to say that angle 4 is the same as angle 1. That would be vertical angles. Angle 1 and 4 are vertical angles. But you could also use alternate interior to 5 There's a bunch of different reasons. Okay, so I have a bunch of 60-degree angles out there. Well, if angle 1 is 60 degrees, then angle 2, those form a linear pair. They're a pair of angles that add up to a whole line. So they add up to 180 degrees. And so angle 2 is 120 degrees. And by the same logic as I've already stated, we can come up with all these as 120 degree angles. So through this whole thing, we only have 2 different angle measures. That's a lot. Or not a lot, if you want to look at it that way. Just meaning that these ideas are pretty powerful. Okay? And it really makes any diagram you have quite a bit easier. So I advise you to use some of these ideas. Okay. So now I want to name the relationship between the 2 angles and mainly focusing on the ones that we have up above. There may be a couple, hint, hint, that are from last unit that we never want to forget because they show up that often. So the first one we have is angle 5 and angle 7. 5 and 7. Those, if I look at the parallel lines here and this transversal, 5 and 7 are both interior and they're on the same side of the transversal. So they are consecutive interior angles. Okay. The next one we have is 13 and 3. 13 is down here, 3 is down here. I look at those with those 2 parallel lines in this transversal. I look and see that they're both in the bottom right. That's kind of the idea that we went with corresponding angles. So those are corresponding angles. Next one I have talks about angle 1 and angle 4. Well, to make angle 1 and angle 4, and this gets a little bit weird, but to make angle 1 and angle 4, I only need these 2 lines. So anytime I only need 2 lines, there's no parallel line that really makes up angle 1 or angle 4. So this is kind of a throwback. It's an older definition that we've had. Okay? It talks about vertical angles. They share a vertex. They're across from each other when 2 lines cross. So we can't forget about those old definitions that we've had. Okay? The next one talks about angle 3 and 11. So I'm dealing with angle 3 again and angle 11. Those are inside of the parallel line, so they're interior, and they're on opposite sides of the transversal. So they're alternate interior angles. I'm going to mess up my own abbreviation, I guess. Alternate interior angles. Okay, the next one we have is 11 and 14. 11 and 14 are formed by these 2 lines crossing, and that's it. And we have 11 here and 14 here. They're not vertical angles. They're not across from each other. They're not across the vertex. They're right next to each other. And they form a line. They're a pair of angles that form a line that makes us think about a linear pair. Again, that's a throwback answer, okay, but we can't forget about it. The last one we have is angle 2 and angle 8. So we're up here and we're down here. Those are outside the parallel lines on opposite sides of the transversal. Sounds like alternate exterior angles. The last thing I want to look at is I've taken that same diagram, made it a little bit bigger, maybe a little easier to see, I don't know. And I've given us 2 angle measures. And from those 2, I claim we can find all the other ones. I'm going to throw a reason out there for each one of them. Okay? And I'm going to kind of show you how I would work through it. I'm going to start with the 38. Well, angle 10 is across from it, so it's also 38. Okay, not too bad. That's a good start. Angle 5 is corresponding. It's in the bottom left, just like 38's in the bottom left. So it's the same. Angle 2 is an alternate exterior angle to the angle measured 38. So it's also 38. And I might be done with 38s. Okay. I would probably look from there that like, did that purple thing again. Looking right here, that angle with the 38 in it and angle 9 form a linear pair. So that means angle 9 has to add up with 38 and make 180 degrees. That's going to be 142. Well, if angle 9 is 142, its vertical angle, angle 7, is also 142. And that might be it for my 142s. I would know like angle 3 and 4 probably add up to 142. Same kind of thing with like angle 1 and angle 6. But that's about all I get there. Okay. For my next trick, let's start dealing with the 62s. I've got a 62 here, so its vertical angle is 62. Okay. From here, its alternate interior angle is 62. It's a different way than I looked before. Okay. Angle 3 and angle 6 are vertical angles, so its vertical angle is 62 degrees. And I think I'm done with 62s. Okay, not too bad. The next one I would look at is maybe like angle 12. 62 and angle 12 have to add up to 180 degrees. That sounds like 118 degrees. I would probably use a calculator for that and the 142. I wouldn't say don't use a calculator. If that one's 118, this one's also 118. So really now I only have angles 1 and 4 left over. Now how could I figure those out? I would look at those and whichever one you wanted to look at, angles, I'm going to say 6, 1, and 2 make a straight line. So those three added together have to equal 180 degrees. Well, luckily 62 and 38 add up to 100. 180 minus 100, that has to be an 80-degree angle in order for that to work. If that one's an 80-degree angle, its vertical angle is an 80-degree angle. And you could have gotten that from the bottom also. From angles 3, 4, and 5 would add up to 180 degrees. So hopefully you made a little sense out of that. If you have any questions, make sure to let me know. Otherwise, have a great day, and we'll see you in class.